So good morning, everybody. Thank you for coming to physics today, even though you probably didn't want to, because outside it feels like negative 30. And it's a beautiful day out, North Dakota weather. And 2 days ago we had what we might call an ice shower or ice storm, and then we got snow on top of that. So I thought it would be a good thing to talk about friction today, because a lot of cars and people could have used that. How many of you guys out there know somebody that got in an accident or slipped and fell in the last couple of days? Okay, so that's about half the kids out there. And I do too, so kind of a sad thing. So, we need to talk about friction. So think of a world without friction. I mean, it's pretty easy to do it now, right? Would you be able to move anywhere?
That depends if you were in Bush right away.
Okay, so that's a good question. So like if there's a wall here, which I'm not exactly sure how that would all work out, having a wall in the middle of somewhere if there's no friction in the first place. I had to think about that for a while. But you know, if you were a person and you pushed on the wall, could you move?
Yes.
Yeah, right? Because you would force on the wall, and in turn, the wall would force on you. We're going to talk about that tomorrow. And you would have a net acceleration in that direction according to the force you applied and your mass. So you can slide across, you can move. Just think about it, out in space, you know, I don't know if any of you saw the latest space movie called Gravity, but you know, there's no friction in the air of space. But I guess that wasn't the reason why I said that analogy is you could tell when people pushed on stuff, they moved. And the things moved as well too. So we could move, but the question is, how could you stop? Well, you'd have to run into another wall, right? And that never works out very good because you fall over when you hit the wall, right? Now the whole question about how the wall is there, I'm not sure how that all works out. But one thing I do know is everything is more fun with a little friction, right?
Yes.
Can we say a little friction is good for everybody? Yeah, in fact, we can say that friction is fun.
Wow.
Okay? So this is the equation for friction. You might want to write that down. That's why I say it's fun, because it looks like a U, but it's really just a mu. Okay, so what in the world does this mean? Well, it's less than or equal to. You want a better description than that? Okay, let's look at this. We've got a box. Okay, and let's say that the box is 40 newtons in weight. Right now, can you tell me what is the normal force on that box? Andrew.
40.
Very good. The normal force is 40 newtons, right? Because we have all gravity here, which is mg, which is 40. And in order for that to not fall through the surface, it has to apply 40 newtons, which is the weight, right?
So if there wasn't 40
But here's the real question. Look, I got a V sub naught that's equal to 0, and our definition of friction is it opposes motion or potential motion, right? This is not in motion. The normal force is taking care of the potential motion of gravity. So, does this thing have any friction on it? No, it doesn't, because there's no motion and there's no potential motion. Does that make sense? Okay, so let's go a little further. Let's say that I push on this here with the force of 5 newtons. Now is there potential motion? Yes, right? Okay, so now we got to figure out if friction is maxed out. Because when friction is maxed out, we write it friction max is equal to the coefficient times the normal. Okay, so that would be the equal part. But friction will only be there as much as it needs to be. It's not going to ever be, well, I shouldn't say it's not going to ever be the largest force, because it can be if something is just slowing down only under the friction of gravity, normal, or under the influence of gravity, normal, and friction. But you're not going to make anything move or accelerate more with friction in a positive direction. Nothing's ever going to speed up friction. So, the thing is, we want to figure out, is this 5 newtons enough force to overcome friction in order for this thing to start accelerating? So what you want to do is just figure out the actual coefficient times normal. Now the coefficient is a rating that describes the relationship between two surfaces. So in this case, it'd be the surface of the floor, the surface of the box, and we'll just say that the coefficient of this is equal to 0.25. Okay, so the coefficient is equal to 0.25. Okay, there's going to be many different kinds of coefficients depending on what surfaces we're talking about. And in fact, many times there's no there's no average coefficient for all kinds of wood and stuff like that. Because think of wood, it has much different grains. It's organic, so it's going to be different per two surface interactions. Okay, so the force max that we'll get here then is the coefficient times the normal, so 0.25 times 40. So we can see that the friction max is 10 newtons. Anybody have a question about that? So, to try to pick up where we left off, because I'm a little unsure what we were talking about, but I know that we have 10 newtons as a max of friction. But does it need to have 10 newtons of force? Because look at this. If I put friction in this direction, which I would because it opposes motion or potential motion, and I said it was 10 newtons, that would give me an overall net force in the direction of friction. But have you ever thrown dirt into the engine of your car? Got something out of it? Probably not, right? So friction doesn't ever do any good that way. Friction can't. Now, if this thing was already moving, then friction could slow it down more. But if it's just stationary, friction is going to be, in this case, less than the max. What do you think friction is going to be? 5 newtons. Because it will match this force to stop that box from being moved. It'll match that to stop it. It would never be greater to accelerate it unless this thing was already moving. Does that make sense? So in this case, friction isn't equal to, but it's less than the coefficient times the normal. So the question is, how do you know that it's not less than 5 newtons, right? Well, according to the formula, you wouldn't know that, but this is where the whole understanding of the physics is. Okay, so let's say that I push with 1 newton, and we forget about this part up here. How much would friction have to push back in order to keep this thing still? 1 newton, right? So now it would be less than 5. What if I pushed with 11 newtons in this direction? How much would friction then push at? In this case, it would actually be 10 newtons because now it's finally maxed out and it can't push any more than that. Yeah, so now in this case, the box is going to actually accelerate, okay? And how much is it going to accelerate? Well, the summation of forces causes the mass to accelerate. Our acceleration is 11 minus 10, right? Divided by 1 kilogram. So it's going to accelerate at 1 meter per second squared in the direction of the push. So the question was, why does it max out at 10? Well, because we've described the relationship between the surface of the box and the ground to have this coefficient of 0.25. Now, if it was rougher, if it was harder for you to move the box, then this coefficient might be, 0.5 or 0.4 or something like that. And then it would max out at a higher position or a higher amount. Okay, I screwed up there. This should be 4 kilograms. I was wrong about that. So 1 divided by 4 is going to be 0.225. 0.225 meters per second squared. So thanks for those questions because 0.25 meters per second squared. Thanks for asking those questions because I was doing a little bit too much in my head here. I was looking at 10 newtons as the weight, which that wasn't the weight. The weight is actually 40 newtons, right? And we know that weight is equal to m times little g. So 40 divided by 10 is going to give us a mass of 4 kilograms. So I messed that up, and that's where that goes. Thank you very much, I appreciate that for those of you helping out there. What we just demonstrated was we had that book on a ramp, and we had theta, right? And let's just give that a degree. Okay, let's say that this thing weighs, well, let's stick with 40 newtons. Okay? And let's say that the coefficient of this situation is 0.33. Okay? So the question is this thing going to accelerate down the ramp or not? And what is the force of friction? So we'll go like this, friction, and then we'll do acceleration. These are the two things we're looking for. Okay? Now I will tell you with most items, as they go from a static friction, which means it's actually not moving, to a kinetic friction, the mu changes. Okay, so usually on items like this, when you have static, it's bigger than when you have kinetic. Now, if you're in fluids like air, like if you're going to space and stuff, get through the atmosphere, that is reverse. The friction gets much, much more as you have a greater velocity. But with these, this kind of interaction, the friction is less. So, first thing we need to know is, what is friction going to max out at? Okay, so it's going to max out at the coefficient times the normal. So in this case, it's going to max out at 0.33, and the normal here is going to be the cosine of 30 times 40, okay? So let's look at that a little closer, because I know we're just fresh on this. But if we look at the force, the part of gravity that wants to push this thing down the hill, that's sine theta mg, right? And then the other part of the triangle is perpendicular, which fulfills our first definition of the normal. And since it's directed into the ramp, it fulfills our second definition of the normal, which is the amount that the surface has to push up on the object in order for it to not fall through the surface. So this is the normal, right? But it's equal to this piece in magnitude, so the normal is cosine theta mg. And I think we have it under notes. Remember we took all our notes on the free body diagram? Okay, so we can see what the max friction is going to be. So 0.33 times the cosine of 30 times 40 is 11.43. What an awesome number for friction. So that's the max. Now the question is that what it takes to keep this box from sliding down the ramp? Because if it doesn't, friction is less than that. Right? Just like on the paper, it didn't move, but we saw that friction must be increasing as I change the angle. So let's see, what force does this have to fight off, you guys? What is the force that's going to push it down the ramp? Well, this is the amount of that gravity that wants to move it down the ramp. So friction cancels that out. There's going to be no movement. Do you agree? So we already know friction is going to be, up the ramp, as long as this has a v sub naught of 0. So the question is, how big is this? Well, this is sine theta mg. That's this, right? Because theta is here. We talked about that angle a long time ago. And this is what you guys, this is the formula that you guys came up with. Remember that? Okay, so this is sine theta mg. So in this case, it's 20 newtons. Do you agree? So that's equal to 20 newtons. Okay, what did we max out at? We maxed out at 11.43. So now we know friction is maxed out. So now we can put the rest of our free body diagram on, and it's going to be like this. And of course it's going to be shorter, right? Because size indicates magnitude, or the how big the number is. So now we have our total free body diagram of these three items. Okay, are we going to have acceleration? Yes, we are. And we know that our friction is maxed out at 11.43. So we'll say that our acceleration is equal to the summation of forces divided by the mass. And in this case, the summation of forces is sine theta mg, which is down the ramp, so it's 20, minus the friction that's opposing it, 11.43, all divided by 4. Did I get that number right this time? Okay, so our acceleration down the ramp then is 2.14 meters per second squared. Okay, any questions about that? So if we wanted to find velocity at the bottom of the ramp, then we would have to know a distance that it's going to move. Let's say it's 2 meters. Okay? And we have an acceleration of 2.14. So v squared equals v sub naught squared plus 2ax. V is the square root of 2ax since our initial velocity is 0. V is the square root, in this case, of 2 times 2.14 times 2, which is equal to the square root of velocity is 2.93 meters per second at the end of the ramp. So let's try one more. Let's say that we have the same ramp at 10 degrees, and we have the same box, 40 newtons. Let's say that our coefficient in this case is 0.5. So let's see what we max out at. So the force max is going to be the coefficient times the normal. Force max in this case is 0.5 times the cosine of 10 times 40 is, cosine of 10 times 40 is what? 39.39, okay. So we have 39.39. So our friction max here is going to be almost 20 newtons. Do you agree? Almost 20 newtons. Let's figure out what the part of gravity is that's pulling us down the ramp. Okay, so it's going to be the sine, in this case, of 10 times 40. And we get our acceleration down the ramp as 6.95 newtons. Okay, so does friction max out this time? No. So in this case, friction is actually equal to 6.95 because that's all it needs to be equal to stop this box. That's the whole less than or equal to thing. Okay, acceleration is 0 because the summation of forces is 0. Okay, any questions about that? Okay, so we're going to pick up here tomorrow. We're halfway through this discussion.